Hello, good evening student. Welcome our channel, the one and only physics point. And in this lecture, we are discuss the new points in the chapter current electricity. This is the Wheatstone Bridge. In the previous lectures, and this is the introductions and first lectures of the new chapter, that is current electricity from the 12th standard physics. In these lectures, we have studied the two laws about the Kirchhoff's, and these laws is indicated the Kirchhoff's current law and Kirchhoff's voltage law. And what are the parameters which are included in that law? That is junction, loop, branches, something. Then the Kirchhoff's first law or law of current or Kirchhoff's current law. This law is also known as the law of junction. In that laws, we have discussed the algebraic sum of electric current at the junction is must be 0. That means the amount of current is arriving at the junction is must be equal to the amount of current which are leaving from the junction. And the second point is the law of voltage or the second law of Kirchhoff, that is the law of voltage. This is the statement about that law is the algebraic sum of potential difference. The potential difference is the product of electric current and resistance. These are given by the Ohm's law. And EMF are produced by the battery is must be 0 in a closed loop. This is all about the Kirchhoff's second law. Statement and some introduction part will be discussed in the previous lecture. And this is the lecture number 2 of the current electricity. If in this lecture we study the Wheatstone Bridge. What is the Wheatstone Bridge? How it can be worked, and what is the applications of the Wheatstone Bridge? Why we are utilized? Why we are importance of the Wheatstone Bridge? Why we are utilize the Wheatstone Bridge? Calculating the amount of resistance which are connected in parallel in the bridge. That is Wheatstone Bridge. Wheatstone, it is one of the scientists who created the bridge for the calculating the resistance which are connected in a bridge or which are connected in the quadrilateral manner, quadrilateral circuit loop. Wheatstone Bridge. Construction and working of the Wheatstone Bridge. Construction, please take the heading, there is construction of the Wheatstone Bridge. The four resistance P, Q, R and S. The four resistance F, four resistance P, Q, R and S are connected in quadrilateral A, B, C, D. Let's draw the construction. This is the quadrilateral A, B, C, D. Quadrilateral A, or this is the point A, B, C, and this only point is D. And the resistance are connected. The resistance, consider the resistance in between the branch A to B, the resistance P, the resistance from the B to C, the resistance Q, the resistance in between the C and D is the resistance R, and the resistance in between the branch A and D is the resistance S. These four resistance are connected in the quadrilateral, that is the P, Q, R and S. The potential E, the potential applied, the potential difference applied across, that is AC, across the AC, and the potential difference is connected, and which is connected across the AC. This is the potential difference which are connected across the AC. This is the higher potential, and another one is the lower potential. The current is must be flow from the higher potential to the lower potential. In between the branch BD, in the branch BD, in the branch BD, the galvanometer are connected. The galvanometer is connected. Galvanometer is connected. This is all about the constructions of the Wheatstone Bridge. These are the galvanometers connected in the cross. And we know that the current is always flow from the potential difference. If the potential difference are applied across the two ends of conductor, then the current is flow from that conductor. That means if the B and D having the same potential, that means the current is does not flow from the galvanometer. That means the galvanometer doesn't show any deflection because the current is doesn't flow through the galvanometer. The reason is not a potential difference across these two ends of galvanometer because the two ends of galvanometer B and D having the same potential. Then what is the working? The working of Wheatstone Bridge, WB, working of Wheatstone Bridge, how it can be worked. In the first loop, ABDA, in a loop ABDA, in the loop A, B, D, and A. This is the first loop. The I1 amount of current flowing through the resistance P, Ig amount of current is must be flowing through the galvanometer, and I2 amount of currents is flowing from the resistance S. As similar, again one at that place the current will be distributed. This I amount of current is flowing from the at the point A, and at the point A is I amount of current will be split in two parts, I1 and I2. That must be equal to, these are I equal to I1 plus I2. I amount of current is flowing from up to the point A. At the point A, this I amount of current is splitting through two parts, that is I1 and I2. When this current is flowing in such directions at the point B, these I1 currents is again split into the another one path and Ig. That means the current flowing on the branch B to C, or the current flowing through the resistor Q, the current flowing through the resistance Q is must be equal to I1 minus Ig, because I1 amount of current is at the point B, but Ig is split from the I1. Then the current is flowing through the resistance Q is I1 minus Q, and these current are continuously flowing from that, and the B points the Ig is added in the I2. At the point D, the Ig amount of current is added in the I2. That means I2 plus Ig amount of current is must be flowing from the resistance R. In the first loop, we know that the directions of current is like that. That means the directions will be shows the flow of current. If anything is opposed to that current, or loop is opposed the current, that means they take negative. If the loop is added to the current or in the same direction of the current, is taken positive. I1 current and P is a similar direction of loop. This must be taken positive. I1 P, and second one is Iz plus Ig minus I2 into S. I2 into S. This must be equal to 0 from the second law, Kirchhoff's second law. In the loop, in another one loop, in loop, that is BCDB, loop B, C, D and B. This is the another one loop, B, C, D, B, and the current is flowing like this. That means the I1 minus Ig into Q is plus Ic minus, sorry, that is I2 plus Ig into R. This is must be positive, and this is a negative, and another one is positive, because the current is flowing from that. This is the direction of flow of current, but we are taken the opposite direction of loops. That means I1 minus Ig into Q, I1 minus Ig into Q minus I2 into Ig, I2 plus Ig into R minus Iz is equal to 0. This is the equation number second. And when we are studying the balancing condition, in the bridge is under the balancing condition. That means the not current or zero amount of current or no current in the fifth resistance. The most important points, if the if the bridge is under the balance or bridge is under the balancing condition, bridge is under the balancing condition, no current flow, no means not, no current flow through fifth resistance, fifth resistance. When if the bridge is under the balancing condition, that means no amount of current or no current flow through the galvanometers or no current flow through the fifth resistor. That means the amount of current will be P and Q is must be equal to amount of current is S and R. Okay. Now in special condition, in special case, if the no amount of current will be flowing through the IG, that means from the galvanometer, that means IG equal to 0. No amount of current will be flowing through the galvanometer, that means IG must be equal to 0. Then the equation first becomes, when we put the IG, this IG equal to 0, that means equation 1 will be I1 into P minus I2 into S, that is equal to 0. Then I1 into P, that must be equal to I2 into S. This is the equation number 3. And as similar to in the equation number second, these IGs must be equal to 0 and this one IGs must be equal to 0. Then I1 into Q minus I2 into R is equal to 0. Then these negative signs are changes into the positive when they are moving opposite directions of the equality sign. Then I1Q must be equal to I2 into R. This is the equation number 4. Equation number 4 and equation number 3. When in a special condition or in a special case, the zero amount of current will be flowing through the galvanometer. That means Ig must be equal to 0. The Ig equal to 0 put or substitute in the equation number 1 and equation number 2. We get the new equation, equation number 3 and equation number 4. Then, this is the last point will be written in the box. And the final equations of that equation, that points, divide, this is the transition state in the given derivation. Transition state means after that state the value will be changes, or this state is most important to remembering because these are the transition state, as well as this is the important to complete the answer. Divide equation 4 from equation 3 or divide equation 3 by equation 4. We know that dividing the I1P upon I1 into Q, that must be equal to I2 into S upon I2 into R. The I1 gets cancelled, I2 gets cancelled, P upon Q equal to S upon R. This is all about the Wheatstone Bridge. It is one of the bridge. We have connected 4 different resistors P, Q, R and S in the quadrilateral A, B, C, D. The P resistors are connected in between the branch AB, Q resistors are connected in between the BC, and R resistors are connected in between the DC, and S resistors are connected in between the AD. Then through the branch AD, we are connected galvanometer to detect the amount of current flowing through that resistance or that branch of that bridge, and what is the amount of current or show the deflection of current or direction of the current when the current is flowing from A to C or C to A, anything. And across this bridge we are connected the potential difference, the A having the high potential and C are the low potential. When the current is always flow from the high potential to the lower potential, that means the current at the point A is a maximum current. The I amount of current is continuously flowing up to the point A. At the point A, I amount of current is split into two, that is I1 which is moving towards to B, or which are also passed through the resistance P, and I2 amount of current is passed through the resistance S. Then this I1 amount of current is again splitted at the point B. This I1 amount of current is splitting into the Ig. This current is flowing through the galvanometer. This is not a special condition. This is the general condition to understand the flow of current. Then these Ig amount of currents will added in I2 at the point D, and the I2 plus G amount of current is flowing through the resistance R, and I1 minus Ig amount of current is flowing through the resistance Q. And by the equation or the Kirchhoff second law of motions, we the algebraic sum of electric potential or potential difference or product of the potential difference across in a closed loop is must be equal to 0. We consider the ABDA, it is one of the closed loop. Consider ABDA in that I1 into P. This I1 and P are moving in the direction of loop. Then I1P minus into I1P plus Iz minus I2 into S, because the I2 is the direction opposite direction of loop, because loop is moving upward direction from D to A and current is flowing from A to D in the resistance S. That means I1 plus P, I1 into P plus IQ, sorry, this is not IQ, Ig minus I2 into S is must be equal to 0. And the second equation is the second condition in a loop BCDA, loop BCDA. These are the loop and direction of loop. That is, the I1 minus Ig amount of current is flowing from the resistance Q, and I2 plus Ig amount of current is must be flowing from the point or resistance G, resistance R. Then these equations with using or according to the Kirchhoff second law, I1 minus Ig into Q, because this amount of current is flowing from the first one of the resistance Q, I2 plus Ig minus I2 plus Ig into R minus Ig must be equal to 0. In a special condition, if the bridge is balanced or the balancing condition of the bridge, that means the zero amount of current is flowing from the fifth resistance, or zero amount of current is flowing from through the galvanometer. That must be Ig, the value of Ig is 0. Then put the value of Ig equal to 0 in the equation number 1 and equation number 2. We get the new equation, that is I1P minus I2 is equal to 0, because Ig is 0 in a special condition. In the equation second, this Ig must be 0, then I1 into Q minus this Ig must be again 0 minus I2 into R minus this Ig is again 0. I1 into Q minus I2 into R must be equal to 0. This negative sign is moving opposite to the equality sign, that gets converted into the positive. That is I1P equal to I2S, again I1Q equal to I2 into R. This is the equation number 3rd and 4th. We are arriving new equations to applying the balancing condition of special case. The most important, divide the equation 4 or dividing the equation 4 from the equation 3, or divide the equation 4 by equation 3, that is I1P upon I1 into Q, I2S upon I2 into R. That is I1 gets cancelled in the left hand side, I2 gets cancelled in the right hand side. We get arrive the new equation P upon Q equal to S upon R. These P, Q, S and R, these four resistors are connected in parallel in a Wheatstone bridge. Thank you. In the next lectures, we are discuss the applications of the Wheatstone bridge. These are the meter bridge.